that's you probably have seen before. How many of you have seen the n choose k? You might have, I'm trying to think if you haven't seen it in probability where you would see that. You might have seen it if you had a hyper, teacher that really likes pure mathematics. They might have shown it to you with Pascal's triangle. So close up laptops. Huh? Yes, that's Pascal's triangle. So I wanted to do Pascal's triangle, but I don't have time to do it. I'll show you what it is though. It's if you look at, make a triangle like this. Pascal's triangle is like the one of the most beautiful things in math. So how am I getting these numbers? Well, start out with ones on the outside. Take these two numbers and add them. That's how you get the next number down at the center. These two numbers and add them. That's how you get this number. These two numbers add them. These two numbers add them. These two numbers and add them to get these numbers on the inside. What's really cool about this is that if I have x plus y squared, then what you're really getting, is the coefficients of that binomial squared. So let's forget about the first row, but here this is just if not squared, I want to the n power. So if you have this to the n power, then if I have n is 2, because I'm on the, if n is 1, I'm on the first row. This is the 0th row. This is the first row. This is the second row and third row. ... So I'm going to push that off to the side. It's just delineating the rows. What you have is if you have x plus y to the n, and n is 1, it's just x plus y. Over here, it's x squared plus 2xy plus y squared. Over here, it's going to be x cubed plus 3xy squared plus 3y x squared plus y cubed. So it just gives you those coefficients. And it turns out that the coefficients are of the form n choose k. It's a counting problem. It turns out to be a counting problem. So I was looking through my notes and thinking I would really love to show you this connection because it's so beautiful. But I just think that I'd have to build up a lot more, and we just be doing this till maybe end of November. So I have to stop, even though I don't want to. A couple of really cool things. If you take Pascal's triangle and throw out all the even numbers, you get this beautiful picture called the Sierpinski's gas. It looks kind of like a sponge with holes in it and with a pattern. And I used to love showing little kids that because they can skip count and I can just tell them throw out all the evens and they can see this picture forming on their page. And it's just one of the most wonderful things. And then you can do the same, any prime number, if you pull it out. And take out all the, if you take out all the primes, you get something really cool. So there's all kinds of patterns you see in Pascal's triangles that are number theory related. But that's Pascal's triangle. How many of you have seen this before, the Pascal's triangle? It's really, really cool, isn't it? Oh, and how do you know that if you're going to use this to expand polynomials? I don't know if you're going to be doing that anymore. Like you shouldn't really, because mathematics and all this stuff. But if you really had to expand the polynomials, all the sum of the exponents have to add up to 3. So you can tell what your mixed terms are going to be on the inside. Okay, so let me go back to the case where we did counting, we did a couple counting things. So we did, we already showed in class with proof that there are 2 to the n subsets of an n element set. And I know someone, either one person is watching that video over and over again, or some of you watched it in preparation of your own induction proof. I just might have one fan in here, I don't know, but a lot of you watched the video on this proof that I did for the case of 2 to the n, counting 2 to the n subsets of an n element set. Alex, was it you? You got some popcorn out and said, hey, got your floor together. Be a fun thing to do to plebes, right?
Yeah.
It'd be a great prank. You guys have to watch this. It is awesome. And instead of sending people funny cat videos, send them one of the YouTube videos from class. So what if I had, you also had the thing with the ice cream. You had all these flavors of ice cream and you didn't want to duplicate the flavor. So you had 12 times 11 times 10. So we're going to go back to that. So what if you had children? I'm going to change it from ice cream to children. N of them. Probably get in trouble for this, but you're giving him the candy. Each distinct. And let's assume k is less than n. How many ways could you do that? This is related to your same ice cream problem. You could take that first piece of candy and you have how many different choices to give that first piece of candy to? N. So you're going to have 1, 2, 3, ... n choices. So one kid got candy. Second choice, you have that second piece. How many choices do you have now? N minus 1. Until what happens? You were going to run out of candy. So let's make a formula for the ith piece of candy. I'll wait till you catch up on writing this out. Is everybody tracking? Because I'm not having you fill in the blanks on this. I just give me a little bit of a break, but I want to kind of pull this together so that you say, what was the point of all this? We're doing all those trees and everything. So the ith piece of candy, what that's going to look like. There's a cadet in my topology class. She likes to make little tables and list things out, and I think it's really nice. So if you do piece of candy number 1, choices was n. Number 2, choices was n minus 1, 3, ... The ith one is going to be n minus I plus 1. And you can kind of see that pattern. What's moving? It's this guy right here that's moving. And that guy's 1 less than the number of the piece of candy that you're delivering. So if it's the second piece, that's going to be 1 less the second piece. All right, so if you total it all up, you run out when you're done with the K pieces, and you're going to get K piece of candy is going to look like that. And that happens to be that. I can quickly show that to you in a second. It's not that hard to see why that's going to be true. Just lots of cancellations. You might have seen this before. If you, I don't know if 256 does stuff like this.
K the same as
No, K is not the same as I. I is your runner. So how do you get the formula for the ith one? It's always going to be one less than the number of pieces of candy. When are you going to run out? You're going to run out when you have K pieces of the candy. So it's going to be n minus K plus 1 is your last one. Does this make sense?
Mm-hmm.
So you need that formula if you're going to be able to write. To me, this is more reflective right here. This tells you the person knows what they're doing. This is like mysterious. Okay, good. Josh, thinking it through?
Yeah, I was figuring out.
So what you do is if you take, this is one of those I think you'd prove with induction. So if you took a real combinatorics class and it was a full semester, you'd be proving these formulas using induction. But you kind of have to know why it's happening too. Like as you saw from the one I gave you, you have to know why the third one nested into the fourth one and on and on. So where that formula comes about is if you look at n factorial divided by n minus k factorial and just do the math, n factorial is this. And then n minus k factorial is this. All the way to 1. Well, everything here, maybe I should have written it like this. If you, math has changed a lot from where I was when I was growing up. But, you know, computers were really being used in the classroom, not everywhere, probably in the late 80s started. And some people jumped on them and some people didn't. I think in 1990 is the first time I saw Wolfram alphas. I mean, the Wolfram product. I actually have a nice video where he talks about, he's a friend of mine and he talks about how he came up with it and why he came up with it. But it was like magical. We could watch that too if we want to have time. It's really cool because he's a legend. But you don't need to do this kind of math anymore if you have a computer that can do it for you. But we used to do a lot of these kind of like calculations where you just see like I've got this stuff here and this stuff here and it cancels and you're left with this stuff. The one right before the one you threw out. So that's where it comes from. What you're really doing is you're really counting the number of k element permutations of an n element set. That's what you're counting.
Permutation.
No, it's not the same as a permutation. You got the permutation for your homework. The n factorial is the permutation of n element sets. But this is the kind of problem where you have, I've got 10 people sitting on the bench for a basketball team. How many ways can I form a 5-person basketball team? It's going to be this formula. But it's not realistic, right? Because you could end up with 5 people who are all as short as me. But okay, forget about that. If you could say, I've got such a great 10-person team, I could put any of these 5 onto my team and I'm okay with it, then there's going to be 10 factorial divided by 5 factorial ways that I can do that.
It's different than a combination.
Yes, we're getting to combination. You were almost there with the, you're almost there. Yeah, yeah. I'm tying this together. Okay, ice cream problem. That's the combinations. Is everybody clear with this? I actually use this sometimes when people ask me questions like, well, won't that be really easy to break that code? Like, no, there's this many ways that you can arrange that code. So someone would have to go through all these ways to do it. Or, you know, somebody like people come up with plans and you realize like that's actually a really high number of ways that you can do this. So yeah. I think that's why I don't have any friends. I say things like that and they're like, we're not going to talk to her anymore. Probably shouldn't be talking to your soldiers that way. Is that what you want to do? Because there's 10 factorial divided by 5 factorial ways to do this. Okay. Remember that from the boards? I was actually happy to see you guys come up with that on it's like an easy problem, actually, if you think about it and build trees. Everything's just born out of the product principle. That's what's amazing. You start with product principle and you start proving all these things or seeing these things. Now, what if instead of having ice cream cones that you're making from these 12 flavors and you wanted to now instead say, I've got 12 flavors, but I'm going to buy 3 pints of ice cream from those 12 flavors. How many ways could I do that? How many ways could I get those 3 flavors? It's the same as the basketball type thing. You're going to pull 3 different flavors from that 12 flavor pile. How many ways could you do that? Would it be, let's say I had 12 and I wanted to take 3. And there's a problem here, right? Because in the 12, 11, 10 case, order kind of mattered. Do you get what I'm saying? Like here, chocolate, vanilla, strawberry is the same as strawberry, chocolate, vanilla. So if you just took 12 times 11 times 10, you're going to have too many. You're going to be double counting things. You'll be counting chocolate, vanilla, strawberry as something different than strawberry, chocolate, vanilla. So you don't want that. Does that make sense? So order doesn't matter. But in your 12, 11, 10 case, order didn't matter. Like if you had chocolate as your first one, then you couldn't pull chocolate again for your second one. I mean, you had the order mattering there. So you're going to get more in that case. Does that make sense? Because chocolate, vanilla, strawberry would be different than choosing strawberry first, and then chocolate second and vanilla third. So you're going to have too many counts. What would you have to do to get rid of all those counts, extra counts? How many extra counts are you going to have?
Combination, does it add all alike, or is it like you have a limited number of grab? Like out of your 12 flavors, you grab one and then it's gone, versus like you can have 3 strawberry or 3.
But you're going through what if scenarios, right? Now instead of making a cone where the order did matter, you're now just pulling 3 from the 12 only.
Yeah, I'm just saying if there's like you can grab more of one thing. So like, because I usually think.
No, you can't. There's 12 different flavors.
When you take one, it's gone.
It's gone,
Okay.
right?
Maybe 12 Qs 3.
But why?
It would-
So I don't want to count these two to be the same. Right? I forgot the cadet's name that were sitting up on the dice. There's 3 cadets sitting on the dice. How many ways can we rotate them around?
Oh.
Remember? 3 factorial, right? So there's 3 factorial ways that you can take this chocolate, strawberry, vanilla, and rearrange them around. So I gotta divide by that. You guys were making stories about like the soup was moving around, doing stuff like I got phone calls about, well, what's the soup doing? He's just sitting there. Put another story in it. I would do that too. How many ways can you make a 5-person basketball team out of 10 people? Well, who's the center? And which ones are the guards? It depends. So you have to divide this out because you're counting them. Like if you had 2 extras, you would divide by 2, right? If you had 2 factorial choices, you divide by 2 factorial. So your old answer has to be divided by 3 factorial. Well, you can do the math. It's 220 ways. These numbers turn out to be pretty big, fast. By the way, that's 12, choose 3. So what does this do? Where does this formula come from? Well, you have to divide by the number of permutations of whatever you're choosing your thing in, but it would be 3 in our case. This part here cancels out the bottom part of, just like I showed you before, that I have to I have too much. If I just do n factorial, I'm gonna have too much there. I don't have 12 times 11 times 10. I have 12 times 11 times 10 times 9 times 8. So I need all that 9 times 8 all to go away. So this makes the extra stuff go away. And this one is your permutation. The ways to rearrange the 3 cadets on the decks. That's why. Amazing. These problems come from a book by a guy named Ken Bogart. He always thought that combinatorics should be fun and not a bunch of formulas. And so he developed these problems and then he'd come to the punchline, develop more. I taught out of this for a graduate class and it was wonderful. Like that class loved mathematics because of this book. Unfortunately, the person died in a car accident. And so it was an NSF funded project and he wanted to make it open. So it was open for everybody to see. And so all of this stuff is free. Master teacher for sure.
And so if I don't know what working somebody constitutes, but this is kind of honestly, you said a few lessons ago, an Erdos number. Does that mean that we technically have, if you have a 1? Does that mean?
I have a 2, yeah.
You have a 2, does that mean that we have a 3?
If you publish with me, yes.
Okay, you have to publish.
So every cadet that publishes with me has a 3. I don't think we talk about that. Because the work I do is applied, so I don't think Erdős comes up ever. Okay, any questions on this?
Choose would be.
It's called choose because we're choosing 3. That's the reason they call this n choose k.
Yeah, but the n would be the top.
How many things you have in the original set, and the bottom, the k would be how many smaller subsets you're making out of that original, right? So think of your 10-person basketball team and 5 play. That's a classic problem. They always have it at the beginning of boring combinatorics books.
So it'd be n choose k. You know, at least where n is the total number.
Right.
K is the subset.
Yes. And it's exactly, that's why it's called n choose k. You're choosing k element subsets from an n element set. That's what you're doing. Do you guys think this is cool, or am I like partying up here by myself?
I think this is a better breakdown of it. So I think it was basics.
They want to have, oh yeah, but you're not, there's so much stuff to cover.
Yeah, like we went through it.
Right. So, you went through this? Why?
Not this deep, no, this is like another.
It is really, really
Permutations and
cool to
combinations.
see why this formula is the way it is. Isaac?
Right here represents the number of permutations.
Yes, so do you, like, I think for me, what I'd like to know is, do you understand why this would be, why you have to divide by 3 factors? So, really, what you're doing is you're asking, if I have 12 flavors, how many ways could I choose a 3-element set out of those 12 flavors? And, we knew that this answer was gonna be too much, because I would have counted chocolate, vanilla, strawberries, famous, right? So I had to divide all the possible permutations I would get from every one of those choices. And so that's your problem that you got for homework.
So, n factorial is if you can grab the same item twice, right? You're
Yes.
using- And then the permutation would be you can't grab the same item twice.
No, the n factorial is you're not grabbing it twice, but the order doesn't matter.
Well, it's both, right? Other times.
Yes, that you don't grab it twice, but the order doesn't matter
Yeah.
either, right? So this is too much,
Okay.
right? So you have to divide out all the orderings.
If you can pick the same number twice, it's just,
That's your 12 times 12 times 12, right? That's the chocolate can be on top of chocolate. So that's the 12 times 12 times cells that you did first. All of it's just product principle. Lucas, boring?
Sorry.
I wish I could tell you there's gonna be R coding sometime, but there won't be.